So that was a neat video. The other example enzyme that they mentioned in chapter 6 is this drug, or not this drug, this enzyme called Chymotrypsin. So what it'll go through and do is cleave protein sequences at the carboxyl side of phenylalanine and tyrosine. Okay, so that's what it does. It finds phenylalanine or tyrosine within a protein chain, and then it cuts that protein chain on the carboxyl side of it. Okay, so that's an important distinct aspect on it. It's not just a random arbitrary cut. It's cleaving very specifically on the carboxyl side of the phenylalanine or the tyrosine. Okay, so let's ignore the characteristics of the enzyme for the moment. So if we took a look at, say, this sequence of our protein chain, where would we get our cut? Okay, and as a sort of hint, the two amino acids I showed were phenylalanine and tyrosine. So where would we get our cut? So if we find our phenylalanine, there's our phenylalanine, our tyrosine is there. Where's the carboxyl side of those? So no, we have to realize that there's another amino acid in here. That amino acid is... I think it's glycine. I always get glycine and alanine confused. If this is phenylalanine, then this has to be glycine. So we've got glycine sitting in the middle. So we're cleaving at the carboxyl side of phenylalanine or tyrosine. It's going to be the right side. This is where our carboxyl end would be. We'd be cleaving here. And in this case, we'd also be cleaving out there, which I didn't draw very well because there'd be more sequence out there. But that's where our chymotrypsin would cleave, okay, the carboxyl side of those proteins, or those amino acids. So what kind of common characteristics would you think the enzyme might be looking for to target those amino acids? What do phenylalanine and tyrosine have in common? Whoops. It's got to be targeting that ring somehow or another. Okay? If you look at the rest of the amino acids, maybe tryptophan gets in there, kind of similar with a ring, but it's kind of a secondary ring to the structure, which spatially probably wouldn't fit within the enzyme pocket. Okay? So if we then looked at, say, a protein sequence, so this is where chymotrypsin typically gets used, is that we would take an unknown protein sequence and we'd mix it with chymotrypsin, and it would go through and cut that protein sequence down into smaller pieces. We could then evaluate those smaller pieces. So if this is our protein, where would it end up cutting? So the first thing we'd have to identify are what their one-letter codes are, so I can help you with that. Tyrosine was a Y, phenylalanine was an F. Okay, so where does it end up cutting? So we need to identify those Y's and F's. So we've got a Y there. We've got an F there. So where's the carboxyl side?
Right side.
The right-hand side, because remember when we talked about our amino acids, our definition or our defined space is the left side is always the amino side, which means when we go through to cut, we'd be cutting here, and we'd be cutting here. Okay. And you can sort of see, right? Cut this here. Yeah.
That's funny.
We got to do something with them, right? Okay. So it is very commonly used in our peptide sequence determinations. You take your peptide, you cut it down into smaller pieces, and you evaluate those smaller pieces. You can then backtrack and build a protein sequence out of that. For sure, we used to have questions on that in the online homework. I don't know if I've kept them in there because we don't talk about it a whole bunch. So be aware you might see that come up where they'll say these 4 or 5 proteins cut at this position. Okay? After you've reacted your protein sequence with these proteins, these are the pieces that you have left over. What was the original sequence? Okay? So you would then be backtracking where those pieces are, where they cut, to kind of puzzle piece it back together, back to the full sequence. Okay, kind of, sort of. Okay. So more interesting to me would be going back to our intermolecular forces, like that video was referencing, is looking at what we would expect our characteristics of the enzyme to be. So number one, we figured we need something to look out for that ring. So we would need probably something kind of like a hydrophobic pocket. Yes, we have a hydrophilic aspect here in the tyrosine, but the bulk of that is hydrophobic. So if we went through to look at the enzyme, and this is kind of neat, this drawing goes through and shows kind of the active site residues of chymotrypsin. So we've got a couple things going on here. Within the active site, it's not just something that grabs a hold of the nonpolar side chain, but we also need something that will go through and actually cleave the bonds. Okay? Because that's what it's trying to do. It's trying to split at that. So if you look, and I just pulled this off the internet, so we don't have a slide on it. So if you look, you've got your kind of protein sequence kind of running through the middle. And kind of attempt to highlight that.
Is that middle representing an amino acid?
So that R line, or that R line, that red line now is our protein sequence. This blue circle that I'm kind of drawing on the outside is our chymotrypsin itself. Okay? So it needs to grab a hold of the protein sequence so that it can go through and cleave. So one thing you'll note is if we look off of our red line, we've got that little ring. That's the ring it's actually seeking out and finding. That's our phenylalanine or our tyrosine residue. Okay. The rest of these, or if you look in that pocket, you'll notice you see a lot of glycines. Why glycine? Relatively small, relatively hydrophobic. It's going to facilitate the fitting of a larger group within that structure. If we then look the rest of the way around, we'll encounter serine, histidine, and aspartate. Okay, well, what's going on with those? If we look at that bond, we are trying to cleave through there, okay, at that position, which means I need to replace that nitrogen with something. What should I replace that nitrogen with?
Like something similar, like carbon? No.
So carbon, then it's not an amino acid anymore. So ideally, if we go through and cleave, we want to kind of keep that same reactivity because I still want to be able to use it somewhere else down the line. I'm not trying to destroy the protein or that amino acid. I'm trying to just separate it out of the protein.
So it's another nitrogen because histidine is the basic and it has the...
If it's nitrogen, I'm right back at a peptide sequence.
I guess it's an oxygen.
Running out of options.
Oh, yeah.
It's what it was before we started, before we put it into the protein. It was an oxygen. It was a carboxylic acid. So we need some source of oxygen to come in to attack. Okay. If that oxygen comes in and attacks, then I can potentially kick out the nitrogen. Okay. Here's where we'd go back to kind of our organic knowledge on this. Oxygen is a great nucleophile, but nitrogen's a better nucleophile. So we would need that oxygen to be a pretty good nucleophile. To do so, it would likely need to be negatively charged. Well, a negatively charged oxygen is typically very, very basic. That becomes questionable. Where do we get a negatively charged oxygen to be able to pull that off? Okay? So we need something in there to deprotonate the oxygen so that it could go through and do this attack. Okay? If we push this further, if that nitrogen leaves, it would come off as N-. Also, incredibly basic. Okay? What could facilitate and make that nitrogen want to leave? If it was protonated prior to it leaving. So not only do we need this kind of very nucleophilic oxygen to come in and attack, but I also need to make the nitrogen a relatively good leaving group by protonating it, which would make it acidic and a strong base right next to each other. That seems a bit odd. Okay, so this is where the enzyme can come in and facilitate some of those transitions. Histidine, basic. Histidine will deprotonate serine. So serine had that OH functional group at the end of it. Histidine can remove that hydrogen. You now have a nucleophilic oxygen. That oxygen can go through and attack the carboxyl carbonyl, break that pi bond. And if you remember back to organic chemistry with your carbonyls, you end up forming a tetrahedral intermediate. You've got a carbon now with 4 different bonds attached to it. There's your tetrahedral intermediate. Okay? That oxygen from our carbonyl is now negatively charged, not very stable. But if we look at the rest of the protein, we've got the serine backbone and our glycine backbone with nitrogens. What do those nitrogens have on them? Hydrogens. We can stabilize that negatively charged oxygen through hydrogen bonding. Okay. At this point, I now have the tetrahedral intermediate. I want to kick out some groups. We're going to need to start doing some transferring. Well, histidine just picked up a hydrogen. Okay. Pulled the hydrogen off of our serine. Okay. What did I need on the nitrogen? I needed a hydrogen. So what can the histidine do? A slight bend away from the serine, and now that hydrogen is perfectly aligned with our nitrogen. It can now protonate that nitrogen. Well, now the nitrogen's a good leaving group. What can happen? Our electrons from our negatively charged oxygen come back down to reform their carboxyl, kicking out the nitrogen. And I've now got 2 pieces, sort of. What's the big issue right now? The carboxyl end of my phenylalanine, in this case, is now connected to, it's connected physically to the protein. I may have chased off the rest of that peptide sequence, but now I'm physically connected to the protein, okay, which means it's no longer functional. So now how do we fix that? Well, we're going to fix that because we're in a water environment. Water can now come into the pocket and, facilitated by the same proton transfers, can go through and trade the oxygen of our serine for an oxygen from water, and we can release that other piece. Tons of chemistry happening within that. Okay. You're trading the oxygen from our serine, which is now physically connected to our protein. Water can come in, and again, through a bunch of proton transfers, hydrogen transfers between the enzyme and water, water can come in, attack, and then kick out the serine oxygen.
Would the water also give its hydrogens?
And the water's going to have to shuttle hydrogens around. Number one, it's going to have to shuttle hydrogens back to serine, so serine becomes a good leaving group, okay? Which is also going to be critical because serine started with a hydrogen. It had better end with it, otherwise it's not the enzyme anymore. Okay? So to run this reaction, we're actually taking 2 substrates. We're taking water and the peptide. Okay? Water can cleave a peptide chain on its own. The activation energy for that reaction is incredibly high. It's not easy to do. The protein brings those 2 pieces near each other, and through its interactions can change the energy of those to drop the activation energy down so that we can actually get the reaction to occur. So when we talk about biochem not having organic chemistry, the reason why they say it doesn't have organic chemistry is there's so much junk going on within that, they decide to ignore it and just say it doesn't. Okay. It is organic chemistry all the way through that. Okay. The parts that make it difficult to analyze is in a lot of cases we don't know what's going on within the enzyme pocket itself. We can just see the end results. So we can say, well, we needed water. So water and the protein come into this, or our amino acid sequence come in, and it does some magic stuff, and it spits out the pieces at the end. To do that, we can take guesses at what amino acids would be necessary. Okay? And if we're trying to figure out exactly how the protein works, we can say, okay, well, I think I need a serine, so anywhere there's a serine in my peptide chain, I'm going to change it to something else. Okay? And then I'm going to test it and see if the reaction still works. Oh, it stopped working? Serine was important. Well, then I think histidine's important. So I'm going to leave serine alone, and now I'm going to change histidine. What happens now? Oh, it stopped working? Histidine's important.
You just don't know.
Okay. Imagine that for every individual enzyme, everything matters.
Well, all of the individual proteins are going to matter to the 3-dimensional structure, and that's where you run into issues. So if we're going to start swapping out, we need to swap out something that has a similar, potentially, interactions with its environment, but the chemistry of it needs to change. So our interactions are kind of our forces that contribute to the 3-dimensional structure, and by chemistry I'm saying the bond structure, the acid-base characteristics. Okay? So maybe throwing in a different structure that just slightly tweaks it and prevents it from doing exactly what it needs. Okay. With a massive protein of several hundred amino acids, serine probably shows up a couple, more than once. So we'd want to be a little bit more targeted than just saying, I'm just going to swap serine for all the serines with one thing. Okay. So we'd want a little bit more information behind that. We might look at the sequence and say, well, they all be kind of close to each other. I'm going to guess they're all in the same part. I'm going to pick these 3 serines, okay, and try and target it that way. So it's kind of a neat process in how these amino acids go through and cleave and catalyze these reactions. Okay. So here's another view of it. Okay. This is again in the formation of our nucleophilic oxygen. So what ends up happening? The same enzyme, we're just looking at it at a much larger zoom in. Remember I said aspartate was involved in that? Aspartate will pull off a hydrogen off of our histidine, which helps shuttle electrons around to make the nitrogen of our histidine more basic. By becoming more basic, it can then deprotonate the serine. Now we have the active nucleophile of our oxygen that can go through and start the whole catalytic process. The next thing, these are color-coded. If we look at that picture, the picture over there is our probably coming from an X-ray crystallography image. Red, blue, green. There's our serine. That's the one that did the cleavage. We've got our histidine, and we've got our aspartate. Take a look what's right next to the serine.
Big old groove.
A big old groove where we could possibly slide that R group. Okay. Our phenyl ring. Okay. If we didn't have that pocket there, its potential catalytic activity is then going to change. Okay. Why does it not target other proteins or other amino acids? I mean, glycine doesn't have a big R group, so there's no reason for it to interact in there. Why wouldn't glycine just sit in there and do that? It's likely because the timing for this reaction to occur takes a significant amount of time. Glycine may still fit in that general area, but it doesn't have something holding it there long enough for the chemistry to actually occur. So glycine may sit in there and fit, but then it doesn't stick around long enough for the reaction to occur. Okay. That extra pocket holds the phenylalanine or our tyrosine long enough that the chemistry can actually occur. Kind of crazy, because remember, these things are constantly moving. It's not just fit in, now cut. It's fit in, wait, now cut. Okay? And each of those waits, something is happening. The protein moves, your substrate moves.
As the reaction starts, does that help to hold it longer, or?
Remember, one of the very first things that happened was that the serine attacked and physically was bonded to the protein sequence that you were trying to cut. Once it's physically bonded, it can't move anywhere. It's now stuck. So after the very first step, it's now stuck in location. It's going to have to wait out the rest of the reaction.
But that first step is what it takes.
And that first step is going to take a little bit longer to get through it. Yep. Okay. Which then kind of segues sort of nicely into the section that we're looking at within Chapter 6, which is all kinetics. Okay. So Anna, your chemistry was a long time ago. I forget, did you take 152?
Yeah,
How long ago are we looking at?
a year and a half.
Year and a, okay. And Robin?
I'll figure it
Okay. So everybody's going to be shaky in this section, including me.
I'm not shaking. I got it.
Okay. I can accept that. I'll pass it off to you when we get to that point, and you can teach us. So in our general kinetics review, what we're looking at is now a reaction, reactants to products, and we're trying to evaluate the speed at which the reaction goes. Okay? So there's some ways that we can go through and evaluate this. So if we were going to describe the rate of the reaction, WRT, with respect to A or D. So what would the speed of the reaction be with respect to A? So our speed is our rate. What's going to happen to A over time?
Combine with B, 2, A, C,
Okay, so that's what's physically changing to it, but I can't measure it combining with A. What can I measure of A? I know it's kind of weird.
Yeah.
How much you have available?
How much? Concentration. Okay. So I can measure the concentration of A with respect to time. Well, that's a rate. Okay, almost. It needs to be the change of A with respect to the change of a standard unit of time. So we can do that with our delta symbols. If I wanted to go through and do this for D, okay, I'd end up with something very similar. I can look at the change of the concentration, whoops, I always leave the brackets off. The change of the concentration of D with respect to the change in time. Okay. Well, how should these rates be related? Should they be related?
If A goes down, I imagine D should go up.
If A goes down, D should go up. That's what the equation is telling us. Okay? So somehow or another, these two things have to be related. And we can drop an equality in here. Okay? And as Robin, you just suggested, as A goes down, D should go up. So what would we imagine the sign on the rate of A being? Change in A is A final minus A initial. Time final minus time initial. What would our concentration of A be after the reaction is started? It should be lower than where we started. So the rate for A should be a negative value. What should the rate for D be? A positive value. Because D is directly coming from A, I can then set up an equality here, but I have to take into consideration that constant factor being that A is decreasing and D is increasing, negative. The change in A will be a negative value, but if I drop a negative in front of it, it now becomes a positive relationship, which will be equivalent to the positive relationship for D. Kind of, sort of. So every time we run a reaction, we can monitor the rate of the reaction by looking at how the concentration of one of our species changes. Okay, that allows, and with respect to time. Okay, so we can start to predict something about the rate. Okay. The next part is what is the dependence of the rate on those concentrations? And that's a trickier question. Okay. That dependence is going to determine ultimately our kinetics. Okay. And what we're referencing there would be, let's say we now take a look at our rate. So our rate we can compare, we can get a value for by looking at any value we want. We're now saying what happens to the rate when I compare it to the concentration of any one of my species. In this case, I'm comparing it to A. Okay. There are a variety of responses that can come out of this. Okay. And that's what each of these three curves is representing. Okay. And there's actually at least one more that we don't see all that often, so we won't talk about it. Okay. What's happening in the blue line? The concentration of whatever species that's generating this is not dependent on the rate. So if I change the concentration for whatever that species was, it does not affect my rate. Typically, at least in 152, when we first encounter GenChem, we end up saying that the species that does that ends up being our product. Okay, well, does that make sense? If we start a reaction, how much product do we have? 0. Do we still get the reaction to work? Yeah, so what would be the dependence of the rate on the product? It should be pretty non-existent. Okay? But that's assuming we're starting in GenChem where we don't have concentrations of everything. We only have concentrations of our reactants. When we move into biochem, what happens? We're in a system that has concentrations of everything. Okay? And depending on an individual reaction, our product may have an effect on the rate. We may not see a flat line. Okay? Most systems that we're looking at, our product won't have an effect. Okay? At least we won't look at the mathematics behind it. We'll just kind of talk about what happens or what changes are going to go into it. What happens with the red line? It's increasing. So as I change the concentration, in this case of A, what happens to my rate? It goes up. very, very consistently. It's going up in a linear fashion. Okay? So there is now a dependence between the concentration of A and my rate. Well, does that make sense? If I have a reactant, does the rate of the reaction depend on the reactant? Well, if there's no reactant, can I have a reaction? No. So it makes sense for the reactant to be part of my rate or contribute to the speed of the reaction. Okay? It may not always, but it does seem to have some effect. It should have some effect. The other option is this green line. What's happening in the green line?
Concentration goes up, the rate goes up exponentially.
Okay. When we change the concentration, we are still affecting the rate, but it's not going up in quite as nice a relationship. Okay. That relationship happens to be based off of the square. What happens when I go from 1 to 2? Let's see if we can find a point that's a little bit easier to see. Let's do 3 to 6. If I double the concentration of A, what happens to the rate? I go from maybe 9 to, what is that, 36? Okay. It goes up pretty darn close to the square of the result. So what we're saying is that we've got a strong dependence here. The rate of the reaction is highly dependent on the concentration of A. Okay, or more dependent on it, is the easiest way to kind of look at it. Mathematically, what does that turn into for us? Okay. What we would then do is, based off this information, come up with an expression. The rate will be dependent on some constant, we don't know what that constant is, times the concentration of whatever our species is, held to some power. Okay. If we went through back off that previous curve, let's kind of guess at these. Blue was flat, red was inclining, green was big. So we said D, red and green never shows up on here, but B we'll say is green. What can we predict about those exponential values, M, N, and O? What was the dependence of the rate on D? There wasn't. So what does that mean O is? What does that exponential value have to be? 0. Anything held to the 0 power is 1. So it won't have an effect on the reaction. What about for A?
It's red, so I'd say 1.
It's 1. It's a 1-for-1 relationship. Okay. B, a lot trickier to figure out, but it comes out as 2. So we can end up predicting something about an order of the species by looking at the exponent on the concentration of that species in our rate expression. Okay. A kind of hand-wavy argument to come out of that is now the importance of said species. So if the order of the reagent is 0, it's not important to the reaction at all. It's a bystander. If the order is 1, it's involved in the rate of the reaction and what's causing the speed of our reaction. If it's an order of 2, super, super involved. If it's order 3, pretty much that entire reaction is dependent on that reagent and that reagent alone. Could we theoretically get orders of 4, 5, 6? Yes. When we're referencing these numbers, the best way to think about it is that you're saying that many or that species is involved in the rate or the speed of the step, the rate limiting step. So if I had a reaction that was third order with respect to A, what does that mean? That means I need 3 molecules of A to interact with each other to cause the rate limiting step. That's when all my chemistry is happening. That's the important step. I need 3 molecules. To get up to 4, what does that mean? I need 4 molecules. 5, I need 5 molecules. Okay?
Is the 3 molecules of A determined?
That's kind of our order, a good way to think about our order. So if we have an order of 3, that means I needed 3 molecules to come together to cause the reaction to occur in a single step. Okay? 0's kind of irrelevant, nothing happened. 1, how easy is it to find a single person in the world? It's pretty easy.
That goes back to what you're saying about
Yep.
Is that the two molecules.
Two, I now need
To do the one.
2 molecules to do that one important step. Okay? So how often do we find couples of people?
It's easier.
It's easier than finding a single person?
It's easier than finding three.
Okay. So it's not that hard to find a couple of people, partnered off. How easy is it to find 3 people all working very well together?
Well, difficult.
That starts to become difficult. What happens to get 4?
Impossible.
Okay. Virtually impossible. So why do we not look beyond 3? The odds of getting 3 people to do anything together effectively is so small. Molecules don't even have this kind of higher order thought process of, okay, we need to get together to do this. It's just random crap coming together and stuff happening. What are the odds we're going to be able to get 3, 4, or 5 molecules all coming together at the exact same instant? It is so limited in our probability scope, it doesn't make sense to look at a reaction where we're predicting an order in that fashion.
So conceivably, right, with the enzyme we were just looking at, if it needed 2 molecules of water to complete its whole thing, the water would be the second.
Would be our second order. So if we looked at our rate, yep,
And the other protein would be 1.
or the other protein would be 0.
0.
Yeah. Okay, so what we're trying to do is kind of build this out and determine something about the speed of the reaction based off those concentrations and kind of go from there. Okay. Once we have the rate, we can then predict something about how the reaction occurred. It's not involved at all. It's involved. Okay. I need one of those molecules for it to occur. There's my first order. Or my second order, I need 2 molecules to allow that reaction to occur. So these orders can give us some information about the mechanism of the reaction, how the reaction works.
So why is C talk about it?
Just because I only had 3 examples, that was it. It's
So-
completely arbitrary. With
Okay.
that A, B, C, D example, completely arbitrary.
Okay.
So I didn't talk about C just because I only drew 3 lines.
Okay.
If I'd drawn 4 lines, we could
Yeah,
have
we
talked
have
about
C
C.
in there too.
Okay. How would we determine these orders? So this may be, Mike, do you remember how to determine the orders? Yeah, can we get a little bit more detail than lots of experiments?
The only true way was experimentation. I remember Giletti saying, but you can hypothesize what they would be or something.
Well, the true way is experiment, but what's the experiment? What do you do?
Rate the concentrations of all of them over and over.
You change the concentrations of all the species involved and you monitor the rate with each of those changes. And then you compare the rates to the changes, and then you have to do all sorts of calculations, then figure out what the order is. Okay, or you can calculate what the order is. Big, long, tedious process. We're not going to go through and do that, not even remotely. Okay, but you need to get some idea of where these things are coming from, and that's kind of the origin. So, what's happening when we go through and look at enzyme kinetics? So if we go at our simplest case, this is my bad on plotting. I just picked a bad point, so ignore that point. In fact, I'm just going to erase it, so nobody can make fun of me. Okay, it's more like that. So we've got a red line here representing substrate to product. We take our substrate, it does a reaction, forms the product. We would expect a straight linear curve. Okay? The substrate is going to depend, our concentration of substrate is going to directly depend on our rate. Okay? What happens if we were to now look at enzyme kinetics?
Faster.
Okay? The enzyme should make the reaction go faster. So what would I adjust on this curve?
The rate will go faster. It's gonna go
I'm
faster, right?
steeper. That's what I wanted to hear. We would expect it to go steeper. Should it go steeper forever?
No, it's going to flatline.
Why should it flatline?
Because there'll be a limit to the concentration where there's no more, it's saturated. It can't.
What's saturated? You're right. Why does it flatline?
Because the substrate, I don't know, don't ask.
What's the substrate reacting with? The enzyme. If I have so much substrate, if I have more substrate than I have enzyme, what's going to happen to the rate? It's going to have to flatline. I've now oversaturated the enzyme. The enzyme can't cause the reaction to occur anymore, so my rate flattens off.
If you added more enzyme, it would keep them going.
If I added more enzyme, I could then delay the flattening further on down the road.
So would it flatline, so if the enzyme was all used up, would it flatline to a point where then it would start going up again as if the enzyme wasn't there?
As if the enzyme wasn't there, quite possibly.
Because then it would go its normal rate, but it would just have to flatline to a point where it would go to that, is that?
Yep.
Yeah.
We'll never get there, so don't stress on that. But yes, theoretically that is possible. Okay. One of the reasons why we would never get there is that if we looked at the slopes of these lines, here it's a bit misleading on the slopes. They look pretty darn close. More than likely, that red line slope is probably more like this.
Yeah, there it is. So, okay.
So, yeah, we could theoretically see it change its dynamics to now switch to the substrate curve, but it's so much slower that we don't even worry about it.
Okay.
Well, that's a good question. No one's asked that. So what happens in our last case? Because we've talked about this before. Which enzyme did this? Or protein? Maybe protein helps. Had allosterism, allosteric control. We just talked about it on Tuesday. Rhymes with myoglobin.
Oh, hemoglobin.
Hemoglobin. I couldn't come up with a better word.
Oh, allosteric.
Okay. When we bind one thing, it changes the reactivity and it binds quicker. What would happen on our curve in that case?
Same curve, wasn't it?
Because as it gets
Oh,
more,
and that, it
keeps
was an
changing,
S
you
curve,
get
like.
more
So we're going to
affinity.
go up as we increase concentration. Our rate is going to snap upwards really, really quickly.
To a point,
And then
and
it's
then
gonna
it'll
And then it's still going to have to flatline off because eventually what happens?
It's all bound, it's got, it's forward.
We've fully saturated the enzyme. It can't turn over anymore. Okay, we run into the same issue in both cases. So we've got a standard substrate curve. We have our standard enzyme curve in blue, and then we have this allosteric control in purple. Okay. So that's our first foray into the graphical analysis. You do need to be able to pick these off and image where they're coming from. Okay? So, this is where it's going to get dicey. Started looking through the slides and I wanted to change everything, but I definitely didn't have time to change everything. So, we're going to have to kind of go through it and deal with what we got. Your enzyme reacts with the substrate to form the complex, the enzyme substrate complex. That enzyme substrate complex has multiple different things it can do. Number one, it can go through to reform the enzyme and produce our product. That is our ideal situation. But potentially just as likely, it could dissociate and go right back to where we started. We have the enzyme plus the substrate.
That's like the enzyme we saw earlier, if the correct adenosine or whatever shape molecule went into the groove, it would then go on to be
It would very likely go on to be ENP.
If the glycine one came in there, the next complex, then it would go back.
Very likely spit it back out. Okay? And so that spit out process still happens with, say, tyrosine or phenylalanine in the case of chymotrypsin. It just happens at a much lower rate. Okay? We can put this all together into then one expression. That's this big red expression here. Okay? Enzyme plus substrate will go through to form our enzyme substrate complex. The rate of that reaction will be dependent on our enzyme plus our substrate and the rate constant for that forward direction. Once I've formed the enzyme substrate complex, it can go through to make the product at a new rate, or a new rate constant, that'll be our K2. Okay? Or it could dissociate back to the enzyme and the substrate. That will then be K minus 1. So our 1 is just referencing first step, second step. The positive being formation left to right, minus being right to left. Okay? So we're just trying to classify those things.
Is K
So the numerical value of K minus 1 to K1, is that what you're saying?
Yeah.
No. Those values can be two entirely different things. Yep. And ideally, we wouldn't want it to be the same. Because if it's the same, you're doing forward and reverse pretty much at the exact same rate. Ideally, we'd go to form the enzyme substrate complex at a faster rate than dissociating it. Because if we go faster, then we can increase the likelihood of making our product. Okay. And here's the part that's missing from this slide. If we want to determine the rate of our reaction, which of those steps is going to determine the rate of the reaction?
Wouldn't the whole thing determine the rate of
Okay. All of those are part of our overall rate for the reaction. Absolutely. Which one is the most important? So the example that we could potentially give would be, how long did it take you to get to campus this morning? Okay. You can look at the entire time, but then you can break that entire time up into different sections. Okay. Waking up, showering, eating breakfast, driving to work. Each of those sections took a different amount of time. Okay? So for me, it takes half an hour to drive to work. Breakfast takes me 5 minutes. If I make eating breakfast faster, does that affect my overall rate?
Not as much as if you
Virtually no effect whatsoever. But if I change how fast I drive to work, will that change my overall rate? Yes. So when we're looking at our reaction beginning to end, what we need to be concerned about is the longest step, okay? Also known as our slowest step. The slowest step is referred to as our rate determining step.
Will it vary?
Okay? And depending on what we are looking at, it will change. It depends on the reaction. So our slowest step determines our rate. Okay? And this is often referred to as our rate determining, so that you're aware of the terms. Our rate determining step or rate limiting step. And you may see that referenced as RDS, sometimes as RLS. Typically, if it's abbreviated, you almost always see it as RDS. Okay. But they're both referring to the same thing. We're saying which step is the slowest one to occur. And we really only have two steps. We have step 1 and step 2. Okay. This would then go back to 152 and saying, okay, well, how are we going to decide what's going on with this? What's going to be our rate determining step? Okay. If it's the first one, then I don't care about anything afterwards. Why?
Just your breakfast.
It's going to happen so much quicker at the end that I don't really care about it. Okay, so I would only be concerned about these parts. Okay. Well, what's happening in this first step?
it's coming together.
Two pieces come together. What's happening in the second step?
It's doing whatever it does.
Doing whatever it does. It's breaking bonds. It's making bonds. Bonds. In this first step, we are making forces. Which do you think would be slower? Breaking bonds is going to end up being significantly slower than breaking or making forces. The forces is just, hey, we see each other, okay, that's cool. Bonds is, I'm now ripping electrons away from you, I'm giving electrons to you. Okay? The bond action would very likely be a lot longer time frame than just the general forces.
So in general, K2 would be the rate limiting.
So we would expect that our rate limiting step in this case is number 2.
For just for this case, or in general?
For this case. Okay, and we could apply that same kind of a logic to it. What's happening at each of those steps? Which of those steps do I think would be slower? Which is more difficult or less difficult? It becomes a shaky ground to walk on. Ultimately, you'd have to discover it experimentally. Okay, but what we're trying to do is come up with something that we can at least agree on, sort of, before we turn it into a complete and utter nightmare. Okay? So I'm concerned about this part being my rate limiting step. Okay, so my rate is going to be determined based off of K2. Okay? So we now run into this issue. Well, to determine the rate for that step, I would need to know K2 Okay, well, let's say we can solve for that from experiment, but I would also need to know what? If I solved for the rate of this second step, it's rate equals the rate constant times concentration of reactants for that step. Do you know the concentration of the reactants? All we know are the concentration of the enzyme and the substrate that we put in there. We know nothing about how they were made. What does that mean happens for our ability to solve this equation? We lose all ability. Okay, so in a multi-step reaction, what we'll do is identify our slow step, and then what we have to assume is that all previous steps achieve equilibrium. Meaning the rate of the forward reaction will equal the rate of the reverse. With that information, I can now go through and solve for the rate of the overall reaction. If I do not make that assumption, this is impossible to solve. Okay. Next thing that's kind of important to evaluate is, remember, our rate in all cases is going to be dependent on the concentration of the substrate. Okay, we've already established that when we go back. Let's see, is it on the previous slide? Oh, of course, I had to draw it on. Okay. When we look at the rate of the reaction, is there a dependence on the concentration of the substrate? Yes. Okay. What makes this even more kind of troublesome is that, is there a dependence on the rate or the concentration of the substrate on this first part? If I change the concentration of my substrate, does my rate change? Yes. Lots of dependence. Look at the end part. What happens when I change the concentration of the substrate? There's no effect. My curve isn't super simple. I have two conditions. At low concentrations of substrate, my rate is highly dependent on the substrate. At high concentrations of substrate, there's virtually no dependence on the substrate. Okay? My rate changes. So that means when we go back to this system, that we're going to have two kind of conditions that we need to satisfy. So when we go through and solve this, we need to make sure that our solve satisfies both of these conditions. If it doesn't satisfy those conditions, everything's wrong. So if we take a look at this, our rate, number one, dependent on K2. Why K2? We decided that was our slow step. So both cases, it's dependent on K2. Okay. Under slow conditions, or low substrate concentrations, what are we assuming? Okay. Under low substrate concentrations, it's so low that pretty much there is no substrate present. It immediately interacts with the enzyme. We have formed this fast equilibrium, and we generate, or we convert it all over to the enzyme substrate. So my rate is slow at low substrate concentrations, and it will be dependent on the enzyme substrate concentration. This was the condition we already addressed. We don't know how to solve for that. What happens at high substrate concentrations? Is it dependent on the substrate anymore? No. What is it now dependent on? It's dependent on the enzyme. How much enzyme is there? So now my rate will be dependent on the enzyme concentration, the total enzyme concentration, which I'm using as E sub T for total. Both of these conditions must be true with whatever we go through and solve. Okay, and that's where this becomes tricky, is we'll have to plug in a substrate value that we think is low and see what happens. Plug in a substrate value that we think is high, see what happens. Do we get a result that matches?
So when you said that the rate is slow and the concentration of S is low, that's because even though the graph was much steeper at that part, it was still
It's still lower than our
rate
max.
than when it
Yeah.
was at that.
So its changing of rate, its acceleration, if you will,
It's
is
high,
much, much higher.
But the rate itself,
But the rate itself is still low. Okay. So those are our conditionals that we need to keep in mind after we go through and solve for our whole overall rate expression. Okay. Questions on that so far? Okay. So, our first assumption is that we have to achieve a steady state. Okay. Before we get to our slow step of K2, we have to assume I've achieved equilibrium here. Which means what? Rate of the forward, rate of the reverse.
Steady state is equilibrium.
Equilibrium. So what's the rate of our forward reaction? Well, that'll be K1 times remember, our rate is our rate constant times concentration of our substrate times concentration of our enzyme. Okay. Our rate reverse is a little bit trickier. Why is it a little bit trickier? And I'm kind of standing trying to blur out the equation. Okay. What's happening to the enzyme substrate concentration? I do have the rate of the reverse, K minus 1, but what else is that enzyme substrate doing? It's also going the other direction. So I'm looking at the rate of the formation of my enzyme substrate and the rate of the decomposition of the enzyme substrate. That has to be set equal to each other. So I end up with this now expression. There you go, oh, that simplifies everything so beautifully. Now we understand everything. Yeah, not quite. Okay. So within this equation, we want to attempt to simplify. What we're going to go through to simplify is to group like terms. Okay. And like terms is a bit weird because do you see anything that's really a like term? Not really. Okay. We can group the enzyme substrates next to each other. That sort of simplifies it. Okay. But what we'll then do is take that a step further. We'll group all the species that have concentrations and we'll put them on one side. And we'll take all of our K values and we'll put them on the other. The K value was what? What did we call it? I know I didn't explicitly state it very well.
It's the rate constant.
It's the rate, what's that last word?
Constant.
Constant. What's this one? Constant. What's that one? Constant. What happens if I group all the constants together? I'll end up with a constant. So they don't cancel because we don't know how they work out. But I'll end up with a constant. Okay. So if I wanted to simplify, I can then go through and say, well, I'm going to group all the constants together and I'm going to make a new constant. And we'll call that something else because that makes it so much clearly obvious. Okay. So I skipped all the algebra, but you should theoretically end up at this point after you do the algebra. Right. With that, we've got some things that we can simplify in here. Okay. The enzyme concentration, you'll notice I do not have an E sub T on it. Why not? Is the enzyme concentration changing through the course of the reaction? This enzyme concentration here is changing. The enzyme substrate concentration is changing. If I add those two up, what should it be? It should be the total substrate concentration. I can get a value for that. Okay. I know the enzyme substrate, or the enzyme total concentration. But the enzyme concentration at any given state during the reaction is going to change. So I can't trust that value. I can't find that value. Right? But I can set up an expression that brings in the total enzyme concentration and put that in relationship to all the other enzyme concentrations. With that information, I can then plug in, and of course now it becomes so much clearly obvious what's going on. Okay? So what we've done is just done that substitution, okay, and we end up here. Right? Add some arrows over the top of this. So sub, and we end up with this. Notice that I don't have K2 plus K minus 1 over K1. I've turned it into Km. Okay, capital Km. What is this? This is our new constant. Okay? That constant is dependent on K2, K minus 1, and K1. Okay? But it's going to be virtually impossible to figure out what all those individual numbers are. So instead what I'll do is solve for the grouping of them and call that K sub M. It's M because the people that went through and initially discovered this, Michaelis and Menten, okay, their names begin with M, so we refer to it as Km. Okay. We've now gone through and simplified, if you will, our expression. Okay? We can then rearrange this again into this final expression. Why this final expression?
Because you're eliminating the rate.
If we go back and think about our two conditions of what our rate was dependent on, okay, it was K2 times concentration of our enzyme substrate, which we would never know the value of. We now have an expression to find that value. Okay? Because I know the enzyme total concentration. I know at least my starting substrate concentrations. I do have this Km. That could become a big mess. Okay? But I've at least kind of rearranged this now where I have some more information about what the enzyme substrate concentration is. So I can go back to the expressions I already had, and I can then plug this value in and start to figure out what's going on with it. Okay? And because we love inventing new symbols to represent things, we've entered in two new values. Rate at low substrate concentrations is low. We will define that term to be V for velocity. So it's not too far off, but that's, we are adding that term. It's a lot less letters. So let's give them some credit for that. If we go through and look at the rate, if our substrate concentration is high, what happened to our rate? It flatlined. We've achieved a maximum velocity. We'll call that Vmax. Right? So now let's start to do all the substitutions because I didn't actually stepwise these in. So let's start to drop this. So we've got V equals K2 times our enzyme substrate, which we said was E over T times our substrate over Km plus our substrate. Right? And we also know that Vmax will be equal to K2 times our total enzyme concentration. Okay, so zero order with respect to our substrate. Can I solve if my rate is low? Do I know K2?
You should be able to get Km.
Careful. Km involves K2, K1, K minus 1. Okay. So even if I could solve for K2, I'm then SOL with Km. Km is at least, because Km I'd still need 1 and minus 1. So solving for K2, not going to be easy. So I can't solve that first expression. Well, maybe I could solve the next one. I can't really solve that one either. Well, what things could I potentially get? I can get my velocity. I know my enzyme concentration. I know my substrates. So I'm running into this issue with K2 and Km.
Are we solving K2?
What if I take this expression and rearrange it to solve for K2? What can I then do with that? I can take that, sub into the original equation, and what I end up with Vmax times the concentration of my substrate over Km plus the concentration of substrate. Okay. And believe it or not, with this substitution, it has. Okay. We said K2 was virtually impossible to sub for. Okay. And you may have been right down that same path that Km is going to be virtually impossible to sub for. So I can't determine that value. But let's hold on a second, take a look at what we now have. Okay. I can run an experiment, right? Where I can change the concentration of the substrate and monitor the rate. Is that true? Yeah. I can generate this curve. Okay, in that upper left-hand corner. And I know it doesn't say all those things perfectly, it's got some other terms on it, but we're really just saying this is substrate and this is rate. Which means, can I determine the rate for my reaction?
Yes.
I can determine V. And I can determine V when I know the substrate concentration, because I put those in. So the substrate value is known. V is known. How about V max? How could I figure out what V max was? If I run my reaction for long enough, say, let's keep the enzyme concentration really low, okay, I can then oversaturate with my substrate and I should start to see it flatline out. And it'll flatline out at roughly
Wherever it's,
The max.
at V max, which means
you can find out.
I can solve for V max through my experiment. If we go through and now look at all those values, what's the only thing I don't know? Km. Can I now solve for it?
Now.
Now I can solve for it. I now have a way that relates all of those rate constants now into Km. I don't need to know what they are individually, but I can now predict everything, all of my terms, and now have some information about the rate of my reaction and something about the rate constants, that Km. That's kind of the power behind the Michaelis-Menten equation. And so what we end up with is that final expression. That is your Michaelis-Menten expression. Okay. Which may seem a bit odd to go through all that trouble to figure this out. But we now have some pieces of information that we can then label about the enzyme. We can determine its Vmax. We can determine its Km. Well, we still don't really know what Km is, so we'll have to look at that in a little bit. Okay. But with that Km, I can now potentially do some more information. If we take this a step further, what we'll find is that we can rearrange the crap out of this equation and turn it into something that makes it a little bit easier to interpret. When you look at this curve, is it obvious the relationship? Okay. What is the equation that describes that line? Okay. By your sigh, I'm going to guess no. No, it's not obvious. What if it was this? Would you now be able to interpret some more information off of it? In a straight line format, we can draw a lot more information out of the straight line to do some interpretations. As soon as it's a curved line, the human eye loses track of its ability to interpret. So one of the things we're going to now do is take the Michaelis-Menten equation and see if we can't rearrange that into a linear equation. Because in the linear equation, I can interpret what those values will be a lot easier than having to do the entire freaking experiment. Okay? Because this equation holds true for this whole process. So instead of finding Vmax, running it all the way out and running an experiment where I have all of those data points to match the line, I can just run an experiment that matches just that front section. And I can then predict all of those values off of extrapolation of that line. Okay? It makes life significantly easier in the straight line format. Okay? So, all of this trouble, we got a lot of different things that can come out of this. Okay? The biggest one is this Km. Okay? It's looking at K2, the relationship between K2, K-1, and K1. Okay? What this measures is how tightly the enzyme holds the substrate. Okay? It's the best way to kind of look at it. If we have a very large value, what does that mean? K2 and K-1 are large. if we have a large Km. K1 would be very small. How tightly does our enzyme hold the substrate?
Which one did you say?
If Km is very, very large, what does that mean?
It doesn't hold it very.
It doesn't hold it very well. K2 and K minus 1 split. Okay? We're saying those values are larger, so it doesn't hold on to the substrate very tightly. If Km is very small,
And it does.
it's going to hold the substrate tighter. Is that important? Well, we can relate that back to a selectivity of our enzyme for an individual substrate.
Will affect the rate.
Okay? And it's also going to affect the overall rate of our reaction. Okay, so we can use that as a general guideline for how tight our enzyme interacts with the substrate. Okay. Vmax we can use to relate to something known as the turnover number. Okay, a turnover number is roughly equated to the efficiency of your enzyme. If we take a look at Vmax and we divide it by our total enzyme concentration, we'll end up with our turnover number. How fast does it turn over? How fast does it produce product? The larger the turnover number, faster it spits out product. Okay? Just to be obnoxious, of course, what do they end up doing? They say we can get this expression that gives us a turnover number, and of course, what do they end up calling it? They bring in another term where you use lowercase k, because we didn't have enough k's floating around in our system, and cat, k-cat, for catalysis. Okay? So we can then report some of these values and get kind of a better idea of what each of those things mean and how we can interpret and use them. So someone could go through, run the experiment, we can look at it and say, oh, I know what Km is, I know what the turnover number is. I can relatively quickly summarize the efficiency of that enzyme and what it's targeting and what it's doing, or how fast it's doing it, hence the kinetics. Kind of makes sense? Okay, and I fully expect kind of. The next part is all of our graphical interpretation. Okay? So this was our standard enzyme curve. Okay? Can we come to some conclusions off of this enzyme curve about all of our terms? So the substrate value is always changing, so that doesn't help us out. Could we determine Vmax off of this curve?
Yes.
Where's Vmax going to be?
Up top.
Okay, so up here?
No, where it flats.
Okay, it's going to be much closer to where it flatlines. Officially, it's an asymptote. The line never actually achieves Vmax, it just gets close to it. So if we're going to draw a line on there, we don't want to draw it directly on it. We want to go a little bit above it. Okay, so we can determine Vmax by just looking at some data. Okay, as long as it processes those numbers out far enough. How could we determine, say, Km? That's much trickier to predict. So one option is to go through and try and solve for Km, which I'm not going to do very efficiently, but let's see if I can do it. I want to do it without telling you the answer is ultimately the issue. Oops, minus. I think I did that right. When would I be able to predict Km? And actually I'm going to have to end there because I know they've got an exam right after us. So we've just rearranged this equation. Well, substrate concentration isn't going to fix it, because then what happens with Vmax and V?
You know the max, or you don't know the.
You know Vmax, sure, but you don't know V.
We get to figure it out.
Almost. So it's not exactly